This video begins what most people would consider the most difficult unit of the year, Unit 10A, which is what we'll look at next. In this unit, we will look at using integration to find volumes of revolution. We've used integration to find areas, now we'll use it to find volumes. I say volumes of revolution because what will happen is we'll take some function, we will rotate that function and some area around a line, and that will create a volume. We'll create it three-dimensional. So first off, let's think about a simple cylinder. We know the volume of a cylinder is the area of the base times the height. In general, any type of cylinder is the area of the base times the height. Here's just a weird-looking prism, I should say. So you do the area of the base times the height to get the volume. Well, in our cylinder, our base is a circle, so really the area of our base is a pi r squared times the height to get the volume. This is going to be the basis for how we will find our volumes, knowing that cylinders, their volume are the area of the base, which is a circle, pi r squared, times the height. And rectangular prisms, we know it would be the length times the width times the height, because really that's the area of the base times the height. So what we will do, the technique we will use, in areas, we cut our area up into little rectangles that were two-dimensional. With volumes, we will cut our section, our solid, into slices that are three-dimensional. When we did areas, we made our rectangles get skinnier and skinnier. We will make our slices in our solid get thinner and thinner. As those become thinner and thinner and our number of slices becomes greater, it will approach what our actual volume is. So it's a very similar procedure to what we did with areas, just we're doing it three-dimensionally with volumes. So say you have some weird shape. We can cut this into slices, find the volume of each slice, add them together, and that can approximate the volume of the whole thing. Well, when we did areas, we cut our area into rectangles of equal width. We will cut our slices of equal thickness. So everything will have the same thickness. And then to find the volume, you'll just have to multiply by the area of the face to give you that three-dimensional volume. You can think of like deli meat or a loaf of bread. When you get deli meat and they cut it into slices, you're starting with some three-dimensional object. Then you get a slice cut. It has a little bit of thickness, and then times the area of the face of that slice of meat would give you the volume of that slice of meat that you have. That's essentially what we are going to be doing here. Now, because your shape, the area of the face might vary, we need to think of the area of that face as a function, a of x. Depending where x is, the size of that face might be different. Here's a couple visuals. You can kind of think of it as like a slice of bread. Depending where you make that slice, again, that face might have a different area. So we'll cut it into a bunch of slices. We'll make those slices get really small, and we'll add them all up, and that'll give us the volume of the whole thing. So this is important. In general, the volume of each slice is the thickness of the slice, which we'll think of as delta x, times the area of the face. Now, most of the faces that we'll work with will be circles. So we know the area of a circle is pi r squared, so it'll make it easy for us. Well, when we made our number of rectangles get huge and got them really, really skinny, that eventually became an integral. It's going to be the same idea here. Our slices are going to get really, really thin, and our number of slices will get huge. That will become an integral. As the number of slices gets huge, it'll become thinner and thinner. And we know that we'll end up getting a Riemann sum, as we've seen in previous units, that will then give us an integral. So this is the main idea of what we're going to get. This right here. to find our volume, we'll do the start of our interval to the end of our interval. The dx basically represents the thickness. That's where that shows up in the integral. And remember, that's going to be uniform for everything. And then a of x is the area of our face. Again, we'll be working with circle faces mostly, so we'll have pi r squared in that spot. So it's important to remember that our slices are moving perpendicular to the x-axis in this case. So if you want to draw in an example slice, you draw it in perpendicular to the x-axis, or we'll eventually see to whatever we're rotating around to make it three-dimensional. Because as your slices move, the area of those faces might be different. If you had a constant, then say it would be a cylinder, so then your faces would all be the same. But most of the ones we'll look at will not be the same. Now, it might be easiest just to look at an example. We're going to find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals square root of x from 0 to 1. Now again, this is how we're getting our three-dimensional shapes. We're taking some function, in this case the curve square root of x. We're taking that and the area underneath it. When we rotate that around the x-axis, it sweeps out a three-dimensional shape, which is the volume that we will have. And here is an example of what will happen. Here we have square root of x. I had it go from 0 to 9 just so it's more pronounced so we can see it. The example we'll do is actually just going to be 0 to 1, but I didn't want it to be so crammed in. We're going to take this area and we're going to revolve it around the x-axis. As it does that, notice it creates a three-dimensional shape. This three-dimensional shape is what we are going to find the volume of. Well, our method that we talked about that we'll use to find the volume is we'll cut this up into a bunch of slices that are really, really thin. Those slices will cut perpendicular to the x-axis. What they will create, each slice will be a disk. It will have a little bit of thickness, and then it'll have a circle as its face. So to find the volume of each of those slices, we'll have our thickness, which will end up being our dx in our integral, times the area of our face. Well, our face is a circle, so we'll just do a pi r squared. Now, as you can see, I'm just showing you here, depending where your x is, that face changes. So that's why it's not just a constant. That's why we have to put an actual function in with a variable. So again, what we're going to do, we're going to do an integral where our area function is pi r squared because the face of each of our slices is a circle. And then we'll have dx because that will represent the thickness of each of our slices. So if we go back, first we'll just sketch it for a second. So we're doing that function and the region between that and the x-axis. In reality, what we're doing is we're just taking a little slice here. And that is revolving around the x-axis to create a disk. And we are going to find the volume of that disk. So, the order of things I would suggest to do when finding your integral. First, what are your values? Well, we've got to decide if we're going to work with x values or y values. You always decide by drawing your rectangles. Now, our rectangles, or our rectangles which will represent the thickness of our slice, you always want to draw that perpendicular to the axis that you're revolving around. We were revolving around the x-axis, so a thickness of our slice would be something like that. Whichever variable is represented by the thickness of that slice, that's the variable you'll work with. Well, that little bracket there represents the thickness in our slice. that is a change along our x-axis because it's going to left to right. That means we're going to be working with dx. The reason that's important is because now we're going to have x values for our integral. And our x values are going from 0 to 1. Well, we said our volume of each slice is the area of a circle, the face, times the thickness. Well, the thickness is our dx. We need the area of our face, which is a circle, which is a pi r squared. So we're going to have pi times something squared. Now, this next thing I'm going to show you is going to be very important for the next few units. If we have an xy axis, if you have some length that is coming from the x-axis, by definition of our coordinate system, your y value is how much you move off of the x-axis. The y value tells you how much you move up or down. So if you have some length that is connected to the x-axis, that's really a y, because y tells you how much you move up and down. Likewise, our x value of a point tells us how much we move left or right. So if you ever have a length that is connected to the y-axis, we can represent that by x, because in our coordinate system, x is defined as how much you moved left or right from the y-axis, where y is how much you moved up or down from the x-axis. And you may be asking, where is this going to come into play? Well, we still need to find our radius for our pi r squared. What we need to do is we need to draw in our radius in our picture. Well, the radius is always connecting the axis of revolution, which we had the x-axis, to the edge of our function. So that would be represented by this blue line here. This blue line that I just drew is connected to the x-axis. A distance moved from the x-axis is always a y. So our radius, therefore, would be represented by y. However, when we do our pi r squared, we can't put in pi y squared. That would be putting y here. We can't put a y in that spot because we already determined that we were doing it in terms of x. So what we'll need to do is we'll need to replace y with what we know it's equal to. Well, we know that our function is y equals square root of x. So we won't put y in here. We will instead put in square root of x. Each of those things is the thought process you're going to have to go through this type of problem. First, draw in an example rectangle to represent the thickness of the slice you're doing. The slice is always perpendicular to what you're rotating around. The thickness of that slice, if it's in an x direction, so going left to right, tells you you'll be dx. If the thickness is going up and down, that's a y direction, so you'll have dy. We'll see one of those in a second. Once you determine if it's dx or dy, determine the values for your integral. And that would be the start and end values of either the x's or y's, depending if you determined if it was dx or dy. Next, we'll have, for these particular cases, when we're doing discs, we'll have pi r squared, which represents the area of our face. You need to decide what r is represented by. So draw in your radius. If it is connected to the x-axis, that is defined as a y, because y is how far you move off the x-axis. If it's connected to the y-axis, it's an x. Well, if you can't put in that specific variable, a y or an x, you replace it with what it's equal to, and that would be your function that you're working with. So we had y, but we needed a dx, so we replaced it with what y was equal to, square root of x. And now this should be pretty straightforward. Our pi, because it's a constant, we can pull it out front if we want and worry about it later. Square root of x squared is just x, and we've got dx. Well, x will go up to x squared. We'll have 1/2 out front, and we'll still have that pi. We've got to evaluate this from 1 to 0, or 0 to 1. So we'll have pi out front. We'll have 1/2 times 1 squared minus 1/2 times 0 squared. The 0 will wipe out. We'll just have pi times 1/2, or in other words, pi over 2. What that is saying is the volume of our solid from 0 to 1 when we revolved it around the x-axis is just pi over 2. Okay, here's another picture of that. You got that section. It's rotated around the x-axis. When we make our slices, we'll call those shapes discs. They have a little thickness, which we'll represent as our dx in the integral. And then the face is a circle. We'll do pi r squared, and we'll just have to determine what the r is. Our r was a y because it was connected to the x-axis. But we couldn't put y in because it was a dx, so we knew y was equal to square root of x. Next example, let's take y equals x cubed. We'll take the region that's bounded by the y equals x cubed, y equals 8, and x equals 0, and we're now going to rotate it about the y-axis. So let's get a visual. Here is our region that we are working with. When we rotate it around the y-axis, notice we will get the figure on the right. So we'll do our integral. Our first step is to decide if we're doing dy or dx. Well, you draw in your sample rectangle perpendicular to what you're rotating around. We were rotating around the y-axis, so we've got that rectangle, that slice, drawn in perpendicular to the y-axis. The thickness of that slice would be represented here. That's a change up and down. That's a change in y's, telling us that we're going to have dy. For our values for our integral, we need to look at the y values. In our region that we have, what is the lowest y value? What is the highest y value? Well, our lowest y value is 0, and the highest y value is 8. So we'll go from 0 to 8. And then we'll have pi times some radius squared. Well, if we draw in our radius, your radius should always connect from the line you're rotating around to your function. So that red represents our radius. Notice that is connected to the y-axis. We saw on the previous slide, when you're connected to the x-axis, that's a y. When you're connected to the y-axis, that's an x. And that's by definition of our coordinate system. X is how much you move to the right, y is how much you're moving up. So we're working with an x as our radius, because it's moving from the y-axis. But we can't put an x in there because we're working with dy. So we need to know what is x equal. Where our original equation was y equals x cubed, if we solve for x, we'll just take the cubed root of both sides. So we get x is equal to cubed root of y. Remember, that's the same as saying y to the 1/3. And that'll probably be easier to work with integral. And that's the hardest part, the setup. Once we have it set up, we've been doing these integrals for a little while now. It shouldn't be too bad. So we'll move the pi out front. We're going from 0 to 8. Y to the 1/3 and then squared is really y to the 2/3. And we've got dy. When we take our antiderivative, y will now be to the 5/3, meaning 3/5 has to be out front. We've got the pi out front, don't forget about that, and we're going from 0 to 8. So we'll have pi, we'll have 3/5 times 8 to the 5/3 minus 3/5 times 0 to the 5/3. Well, the 0 will wipe out. 8 to the 5/3. Well, the 3 means cubed root, so cubed root of 8 is 2. 2 to the 5th is 32. Then we'll have to do 32 times 3/5. Well, 32 times 3 is 96, so we'll get 96 over 5, and don't forget about your pi. So 96 pi over 5 represents the volume of our region when we rotate it around the y-axis. So this region here's volume we just found was 96 pi over 5. Next one, we're going to take our region enclosed by the curves y equals x and y equals x squared. So let's see what that looks like. Here's y equals x. Let's call this 1 and we'll call that 1. Now we know x squared is a parabola. What we need to decide is if that parabola is going to dip below or stay above the line y equals x. Well, think about 0.5. The point 0.5 comma 0.5 is on y equals x. But if you take a half and square it, you get 1/4. So you'll have a half 0.25. So that means x squared is going to stay below. And our region that we're going to have is this region right here. We are going to rotate this around the x-axis. Now, this is going to be different from the last two examples. In the last two examples, our regions totally rested against the line we are rotating around. Here's our last one. Notice our region was totally resting against the y-axis. Here's our first one. Notice the region was totally resting against the x-axis. When that is occurring, when we rotate it around and do our slices, that's what created our discs. Because we have this gap now, we are going to have created what are called washers. So watch now as we have a region that has a gap that's rotated about something. I took this little rectangle and I rotated around a line where there's a gap. Well, notice when it does that, it creates not a disc anymore, but something we'll call a washer. Okay, a washer like the thing that you put on before a nut when you're maybe bolting something down. Our washer is a circle with a circle cut out of it in the middle. When we find the area of our face, the area of our face is going to be the area of the big circle minus the area of the circle that's cut out. So we're going to have two radii we're going to have to find. Our inner radius will be the area of the circle that's going to be subtracted off, and the outer radius is going to be the area of the big thing. So we'll take, essentially for our face, we'll do the area of the big circle minus the area of the small circle. We will do this method, the washers, anytime there's a gap between our region and the area we're rotating around. So let's just look at another picture of it here. Here we have our gap. When it gets rotated around, the whole region looks like this. It'll kind of look like a funnel with some thickness to it. And when we do each slice will end up looking like this. So we'll get a washer. So our strategy is still to do our areas of our faces times our thickness, where the thickness is dx in this case. To find the area of our face again, we'll have to do the area of the outer circle minus the area of the inner circle. So again, we're going to do the area of the big circle minus the area of the small circle in order to find the area of our face. So let's go through our process. First off, we need our slices, or the rectangle to represent the slice, remember, always goes perpendicular to the line you're rotating around. We were rotating around the x-axis, so we'll draw it like that. The thickness of that slice changes in the x direction. That tells us that we're doing dx. Now we know that we need to have x values for our integral. Well, we need to know which x values bound our region. Well, our region, those functions intersect at 0, 0, and 1, 1. So that means our x values are 0 to 1. The difference now is for the area of our face. The area of our face, we said, is the area of the big circle minus the area of the small circle. Well, that means we have pi times some radius squared minus pi times some radius squared. Well, the outer radius will come first, the inner radius will come second. The inner radius, let's start with that. That's the one that'll come second. The inner radius is this right here. Basically, the radius that makes the gap. Well, that black line is connected to the x-axis, so we know that's a y. Well, just be careful here. We have multiple y's. That height y is represented by our green function, which really was x squared. So really, that y is x squared. So our inner function that will make our small circle, the radius is x squared. Okay, it was really y, but we can't put y in because it's dx. Now our outer function, its radius is represented by this green line. Well, that again is just a y. It's connected to the x-axis, but we can't put y in because we have dx. Keep in mind now our y is equal to something different because it's a different function. In this case, y was y equals x. So we'll put in x for our radius. So we have pi times a y squared minus pi times a y squared. Our outer y was x. Our inner y was x squared. We've done the hard part. Now we just need to find the integral. So let's neaten this up. We'll pull the pi out front. We're from 0 to 1. We'll have x squared minus x to the 4th dx. X squared will be x cubed. We'll put a 1/3 out front. X to the 4th will be x to the 5th. We'll put a 1/5 out front. Keep the pi out front. We need to evaluate from 0 to 1. We'll plug in the 1 and the 0. So we'll have pi times 1/3 times 1 to the 3rd minus 1/5 times 1 to the 5th minus the whole quantity 1/3 times 0 cubed minus 1/5 times 0 to the 5th. Well, the zeros will wipe out. We don't need to worry about that. And we'll end up with pi times 1/3 minus 1/5. Well, 1/3 can be rewritten as 5/15. 1/5 can be written as 3/15. So really this is pi times 2/15, which would give you 2 pi over 15. And what that represents, that is the volume of this region. 2 pi over 15 is the volume of that region when it was rotated around the x-axis. We're going to take the same region that we just worked with, and we're now going to rotate it around the line y equals 2. Our picture will look something like this. We have our original region here. We're rotating around y equals 2. And what it kind of ends up looking like is one of the cones that they use in gym class. You can think of it as like a cereal bowl kind of, but that has an empty bottom. A cereal bowl with the bottom cut out almost is the shape that we're going to have. So when you cut that into slices, we will have washers. So our line we are rotating around is a horizontal line. So the thickness of our slices is still a dx. When we pick our values for our integral, it is the values of the original region, not after it's rotated around the line. So our original region, we still went from 0 to 1. Because we have washers, we're going to have pi times some radius squared minus pi times some radius squared. Let's start with our inner radius. Our inner radius goes from the line we're rotating around to the one that's closer. Well, the one that's closer now is the y equals x. this squiggly length that I'm putting in here in blue, we know that that should equal y because it's connected to the x-axis. We know that together our green segment plus y should equal 2. The radius that we want, the radius for the inner part, is basically that 2 with that blue y chopped off. So it's 2 minus our blue y. Well, that's really 2 minus our blue y went to the y equals x function. So that's really 2 minus x to represent our inner radius. Now our outer radius will be similar. It's just a different y. Our outer radius, the green part, will now stretch to the outer function, the x squared. That squiggly part is our y, so the green part can be represented as 2 minus the y value. Well, now our y is a different y. It's really 2 minus x squared. And that's your outer. These are much more complicated. It's tricky to figure out what those radii are, and there are some of the harder ones that we will do. Now let's see if we can take our integral. Well, let's pull the pi out front. The 2 minus x squared and the 2 minus x, we're going to have to FOIL each of those. The 2 minus x squared will end up getting 4 minus 4x squared plus x to the 4th minus, now keep in mind this all has to be subtracted. So put it in a parenthesis. We'll have 4 minus 4x plus x squared, and then our dx. So we'll next distribute our negative. We'll have 4 minus 4x squared plus x to the 4th minus 4 plus 4x minus x squared dx. Next, we'll just combine our like terms. 4 minus 4, that goes away. We'll have an x to the 4th. Negative 4x squared minus x squared, it gives us negative 5x squared. And we'll have a plus 4x. And this is just a, this is just a regular integral now. We'll keep the pi out front. We'll have x to the 5th and have 1/5 in front of it. We'll have x to the 3rd. We'll have minus 5/3 in front. And we'll have x squared. We'll have to multiply the 4 by a half, so we'll get 2. And that'll be evaluated from 0 to 1. We'll plug in 1 and we'll plug in 0. So we'll have pi 1/5 times 1 to the 5th minus 5/3 times 1 cubed plus 2 times 1 squared. Minus, when we plug in the 0 is going to wipe everything out, so we can just put it as a big 0 if we want. So this will be pi times 1/5 minus 5/3 plus 2. A common denominator would be 15. So this is pi times 3/5 minus 25/5 plus 10/5. Sorry. 15 was the common denominator. These should each be 15ths. 3/15, 25/15, and then this should be 30/15. Sorry about that. When you add those up, 3 and negative 25 will give you negative 22. Negative 22 and 30 will give you 8. So we'll get 8 over 15, and we'll tack our pi on, telling us that our volume, when we rotated that region around y equals 2, is 8 pi over 15. Each of the things we saw in the examples are called solids of revolution because we got the three-dimensional solids by rotating some function about a line. We could do it in terms of x or in terms of y. When we draw in our slice, which is perpendicular to the x or y axis, depending what you're rotating around, or some line, some horizontal or vertical line, the thickness of that slice tells you if it's dx or dy. If the thickness of your slice moves left and right, then that is a dx. If it moves up and down, that's a dy. Now, we found our area always in one of two ways. If it was a disk, we knew we were working with a disk if our region was totally resting against the line we were rotating around. In that case, we just had pi times our radius squared because it would be a circle. If we had some gap in between our region and the area we were rotating around, that created a washer. So we had pi times the outer radius squared minus pi times the inner radius squared. Those are the two methods that we have worked with so far to find volumes of solids. For the last example for the video, we're just going to prove to you our volume formula for a sphere, 4/3 pi r cubed. Okay, you've worked with that since at least geometry. Well, to get a sphere when you rotate, we're going to start with this function here. It'll go from minus r to r. And the equation would be y equals square root of r squared minus x squared. And where that's coming from is if you have a circle, we know our equation of a circle with a center at the origin would be x squared plus y squared equals the radius squared. Well, all I did is got y by itself, and because we're thinking of it as the top half, when you do the plus and minus, it's just the plus part. Well, we're going to take that, we're going to rotate it around the x-axis, and when you do that, that'll create a sphere. So we're going to use our integration to show that you'll end up getting the 4/3 pi r cubed when you do the volume, because we don't have an exact number for our radius. We're going to do it in terms of r. So we're going around the x-axis, so we'll draw in a slice. The thickness of that slice is in the x direction, so we'll have dx. Our x values are going from negative r to positive r. Remember, r is a constant. That's going to be important. Treat r like you would any number, not as a variable. So we'll do pi times our radius squared. Well, our radius goes from where we're rotating around to the edge of our function. That's attached to the x-axis, so that's a y. But we can't put in y for the radius because we have dx. We have to put in what y is equal to. Well, y is equal to r squared minus x squared. And actually, we now just need to neaten it up before we take our integral. So we're going negative r to r. Let's stick the pi out front. The square and the square root cancel out, so we have r squared minus x squared dx. And again, r is a constant. Think of it like a number. So when we take our antiderivative, we'll have our pi. R squared is a number. When you take the antiderivative of a number, it just gets an x. So this will become r squared x. X squared will be x cubed, and we'll have a minus 1/3. And we're going to evaluate that from negative r to r. So we'll have pi. Plug in r to the first part. You'll have r to give you r cubed. Plug in r to the second part. You'll have negative 1/3 r cubed. Minus, plug in negative r for x. You'll have negative r times r squared to give you negative r cubed. Put in negative r for the x cubed. You'll get negative r cubed times negative 1/3 to give you positive 1/3 r cubed. If we distribute our negative, we'll get pi times r cubed minus 1/3 r cubed plus r cubed minus 1/3 r cubed. Well, these 1 r cubes think of as 3/3. So we have a common denominator. Well, 3 over 3 minus 1/3 is 2/3, plus 3/3 is 5/3, minus 1/3 is 4/3, so we'll get 4/3. You got your pi there, and then we've got r cubed. So we just showed, through calculus, the formula for volume of a sphere. And here's basically what happens. So your slices start out thick, they get thinner and thinner and thinner, and that's what our integral is, those slices getting thinner and thinner and thinner, and that gives us our volume of the sphere then. That's all for today's video. We'll see you next class, period.